Today we are going to discuss about the next topic, Laplace transform. So see the next unit number 3, Laplace transform. So in this lecture we have to start the new topic named as the Laplace transform. Now see here what is meant by Laplace transform, or what is definition of Laplace transform. So see the definition: if f of t is a function of t, then the proper integral from 0 to infinity e raised to minus st into f of t is called as Laplace transform of f of t. So this is the simple definition. F of t is a function of t is the time domain. Then the proper integral from 0 to infinity e raised to minus f of t dt is called as Laplace transform and is denoted as Laplace of f of t or phi of s. So that is Laplace transform of f of t, that is equal to integral from 0 to infinity e raised to minus st into f of t dt, that is equal to phi of s. So see the definition. Value of this integral is nothing but your Laplace transform of f of t. F of t is a function present in integrand, limits from 0 to infinity, that is equal to phi of a. That means these are the limits of t, and if we evaluate this integral and substitute the upper limit as well as lower limit, we get here function of s. That's why we have to denote here phi of s, that means function of s. So this is the simple definition of Laplace transform. So we have to use this definition to find Laplace transform of different types of functions. Okay, now see here how to find Laplace transform of some elementary functions. Okay, now see, next article is Laplace transform of some elementary functions. Laplace transform of elementary functions. So see, first function is Laplace transform of 1 is equal to 1 upon s. So if we calculate Laplace transform of 1, so this is Laplace transform of 1 is 1 upon s. So see here how to find this Laplace transform of 1. So see the solution. By definition of Laplace transform, we have Laplace transform of f of t is equal to integral from 0 to infinity e raised to minus st into f of t dt. So this is the definition of Laplace transform. Now we have to calculate Laplace of 1, so we have to take f of t is equal to 1. So take Laplace transform, take f of t is equal to 1. So we can write Laplace transform of 1 is equal to integral from 0 to infinity e raised to minus st into f of t. But what is value of f of t? That is nothing but 1 into dt. Now taking integration with respect to t, we can write e raised to minus st divided by minus s, limits from 0 to infinity. Now these are the limits of t. So substitute upper limit as well as lower limit, we get. So if we put upper limit, we get here e raised to minus infinity, but e raised to minus infinity is 0. So we get here 0 minus, if we put lower limit, we get e raised to minus 0, that is e raised to 0. E raised to 0 is 1. So we get 1 upon minus s. So that is equal to minus minus plus 1 upon s. So this is the required Laplace transform of the constant 1. So this is the first function, elementary function, which have a Laplace transform 1 upon s. Now see the next function, number 2, Laplace transform of e raised to at, where a is any constant, is equal to 1 upon s minus a. Now see how to find Laplace transform of e raised to minus at. Okay. So see the solution. By definition again, by definition of Laplace transform, we know Laplace transform of f of t is equal to integral from 0 to infinity e raised to minus st into f of t dt. So this is the definition. Now we have to take f of t is equal to e raised to at. So take f of t is equal to e raised to at. So we can write Laplace transform of e raised to at is equal to integral from 0 to infinity e raised to minus st as it is. Instead of f of t, we can write f of t is equal to e raised to at. So this is e raised to at into dt. Now we have to solve this integral. Now see here, this e raised to minus st and this is e raised to at. So base same. So using laws of indices, we can write this as integral from 0 to infinity e raised to minus s minus a into t, that is dt. Okay. So laws of indices, minus sign common. Here st t is also common, so we get s minus a in bracket. So this is the final function after using the laws of indices. Now take the integral with respect to t. So taking integration with respect to t, we get e raised to minus s minus a into t divided by minus s minus a, limits from 0 to infinity. Now substitute upper limit as well as lower limit. So if we put upper limit, we get e raised to minus infinity, that is 0, minus e raised to 0, that is 1, upon minus s minus a. So this minus minus will get plus 1 upon s minus a. So this is your required Laplace transform of e raised to at. Similarly, we can find the Laplace transform of e raised to minus at. That is nothing but 1 upon s plus a. Again, say by definition of Laplace transform, taking f of t is equal to e raised to minus at. So here we get e raised to minus at. Here again we get e raised to minus at. So using laws of indices, here we get minus sign to be common. Here we get s plus a. Again taking integration, we get here s plus a, s plus a. Putting upper limit and lower limit, we get s plus a, and there is nothing but again 1 upon s plus a. So this is the Laplace transform of e raised to minus at. So both are the same. Now see the next elementary function, number 4. Number 4, Laplace transform of cos at, that is equal to s upon s square plus a square. So this is the simple Laplace transform of cos at, that is nothing but s upon s square plus a square. Now see here how to find this Laplace transform. So again, by definition of Laplace transform, we can write Laplace transform of f of t is equal to e raised to is equal to integral from 0 to infinity e raised to minus st into f of t dt. Okay, so this is the definition. Now we have to take f of t is equal to cos at. So put f of t is equal to cos at. So we get Laplace transform of cos at is equal to integral from 0 to infinity e raised to minus st into cos at dt. Now we have to solve this integral, and for that we have to use one formula of integration. All you know about this formula. Here what is formula we have to use here. So using integral e raised to ax into cos bx dx, that is nothing but integral e raised to ax upon b square into bracket a cos bx plus b sine bx. So using this formula of integral, here e raised to minus st, so instead of a we have to write s, and here cos at, so instead of b we have to write a. So we get, therefore we get Laplace transform of cos at is equal to e raised to minus st divided by a square. A square means s square plus b square means a square into bracket a cos bx, that is a is nothing but minus s into cos b is nothing but a into t plus t into sine at, bracket close, limits from 0 to infinity. Now substitute upper limit as well as lower limit. So if we put upper limit here, we get e raised to minus infinity, that is 0, correct. Now we have to put lower limit. So if we put lower limit, here we get 1, e raised to 0 is 1 upon s square plus a square into bracket, here minus s as it is, here cos 0 is 1 plus sine 0 is 0. So that is nothing but this minus, and this lower limit minus plus, we get s upon s square plus a square. So this is the required Laplace transform of cos at. Okay. Now on the similar way, we have to find Laplace transform of sine at. So number 5, Laplace transform of sine at, that is nothing but a upon s square plus a square. So again, by definition of Laplace transform, Laplace of f of t is equal to integral from 0 to infinity e raised to minus st f of t dt. So we will take here f of t is equal to now sine at. So sine at. So therefore we get Laplace transform of sine at is equal to integral from 0 to infinity e raised to minus st into sine at dt. Now using formula of integral, so see here what is formula. Integral e raised to ax into sine bx dx, that is nothing but e raised to ax upon a square plus b square, a into sine bx minus b into cos bx. So this is the formula for integration when function is sine here. So using this formula to evaluate this integral, we can write it as, so therefore Laplace transform of sine at is equal to e raised to ax, but a is equal to minus s is here, so here minus s into t upon s square plus a square into bracket minus s into sine at minus a into cos at, limits from 0 to infinity. Now substitute upper limit as well as lower limit. So if we put upper limit, we get 0 minus, if we put lower limit, we get e raised to 0, that is 1 upon s square plus a square into bracket, this is sine function, so we get 0 here, this minus a into cos 0 is 1, so this minus minus with plus a upon s square plus a square. So this is your required Laplace transform of sine at. So here Laplace transform sine at is what? A upon s square plus a square. Okay, now see the next, how to find Laplace transform of hyperbolic functions. So next is number 6, Laplace transform of cos hyperbolic at is equal to s upon s square minus a square. Now we have to prove this result. What is Laplace transform of cos hyperbolic at, that is s upon s square minus a square. And what is, remember what is Laplace transform of cos at, that is there is plus sign only in denominator. Okay, remember that one, don't confuse here. So see here how to find this Laplace transform. So again by definition of Laplace transform, we have Laplace transform of f of t is equal to s upon is equal to, by definition, integral 0 to infinity e raised to minus st into f of t dt. Now we have to take f of t is equal to cos hyperbolic at. Okay. Now see here how to find Laplace transform. So taking f of t is equal to cos hyperbolic at, so we can write Laplace transform of cos hyperbolic at is equal to integral from 0 to infinity e raised to minus st into cos hyperbolic at into dt as it is. Now here we have to use formula for cos hyperbolic at in terms of exponential function. So what is this formula? We know very well, integral from 0 to infinity e raised to minus st as it is. Cos hyperbolic at is nothing but e raised to at plus e raised to minus at divided by 2 dt as it is. So formula for cos hyperbolic at in terms of exponential. Now use log of indices and take constants to be outside from integral sign. We can write 1 upon 2 is a constant, integral from 0 to infinity, and if we take multiplication and using laws of indices in the same step, so we can write in square bracket e raised to minus s minus a into t plus e raised to minus s plus a into t bracket close dt. Okay. So this is the simplification after multiplication by e raised to minus st with e raised to at and e raised to minus st with e raised to minus at. Now try to integrate this. So we get 1 upon 2 as it is. Taking integration, we can write e raised to minus s minus a into t divided by minus s minus a into t plus here e raised to minus s plus a into t divided by minus s plus a, not t is there, integral limits between 0 to infinity. Now substitute upper limit as well as lower limit. So we get, if we put upper limit, we get 0 minus if we put lower limit. So if we put lower limit here, we get 1 upon minus s minus a, and here minus 1 upon minus s plus a bracket close. This minus minus and this minus minus will get plus. So 1 upon 2, 1 upon s minus a plus 1 upon s plus a. Now simplifying, we get 1 upon 2 into bracket s plus a plus s minus a divided by s minus a into s plus a, that is s square minus a square. Now we have minus a plus a cancel, we get s plus s, 2s, and this 2 cancel, so we get s upon s square minus a square. So this is the required Laplace transform of cos hyperbolic at. Okay. On the similar way, we can find the Laplace transform of sine hyperbolic at. So see here, try this at home. I will give the hint. Sine hyperbolic at, that is 1 upon a upon s square plus, sorry, minus is here, same, s square minus a square. So by definition again same, here we have to take sine hyperbolic at, here we can write sine hyperbolic at, here sine hyperbolic at, here middle sign is change, again here middle sign is change, here middle sign is again change, here minus minus and this minus, so totally here we get minus sign, here we get plus. Now here we get s plus a minus s plus a, so here s cancel, a plus a, that is 2a, and this 2 cancel, so here we get a. Okay. So this is the required Laplace transform of sine hyperbolic at. Try this at home. Okay. Now see next function. Now Laplace transform of t raised to n is equal to, there are two solutions. First one is gamma n plus 1 divided by s raised to n plus 1, where n is fraction, and second is n factorial upon s raised to n plus 1 when n is integer. Okay. So there are two types of solutions for Laplace transform of t raised to n. Now see here how to find these two Laplace transforms for one function. So by definition again, by definition of Laplace transform, we know Laplace of f of t is equal to integral from 0 to infinity e raised to minus st into f of t dt. Now we have to take f of t is equal to what? T raised to n. So take f of t is equal to t raised to n. So therefore we get Laplace transform of t raised to n is equal to integral from 0 to infinity e raised to minus st into t raised to n dt. Okay. Now see here, we have to evaluate this integral. Now remember how to evaluate this integral. What we have to do to solve this integral? Now observe this integrand. So limits from 0 to infinity, exponential function is there and t raised to n power function is there. So if we remember the definition of gamma function, what is the definition of gamma function? That is gamma n is equal to integral from 0 to infinity e raised to minus x raised to n minus 1 dx. So this is the definition of gamma function. Okay. So if we see this integral, we can convert this integral in terms of gamma function by taking substitution for minus st, because here we have to require single variable only. So take substitution for st. Okay. Now taking substitution for st to convert this in gamma function. So put st is equal to new variable, suppose u. So therefore t is equal to u upon s. So dt is equal to du upon s. Now check limits of integration. When t varies from 0 to infinity, u also varies from 0 to infinity. So there is no change in limits of integration. So therefore Laplace transform of t raised to n is equal to integral is same from limits 0 to infinity e raised to minus st. But what is minus st is what? U. So e raised to minus u. After that t raised to n, that is u upon s raised to n to du upon s. Now here function we have to take integration with respect to u. So s is constant. So taking s to be outside. So here 1 upon s raised to n and here 1 upon s. So totally you get 1 upon s raised to n plus 1. Okay. Now remain under integral sign is e raised to minus u raised to n and du. So that is nothing but 1 upon s raised to n plus 1 into gamma n plus 1, because this n can be written as n plus 1 minus 1, okay, into du. So but what is gamma n plus 1? So that is nothing but n factorial upon s raised to n plus 1 as it is. So this is the two solutions for the given Laplace transform. Okay. Now this is the Laplace transform of some elementary functions. We have to remember these formulas because we have to use this formula as it is to solve the problems. So once I will get the table format for these functions or corresponding Laplace transform. So see here we have to remember this for the whole completion of whole topic, because we have to use this as a basic formula to evaluate all the problems. Okay. So here function, tabular form function, here its Laplace transform. Okay. So see here number 1, its Laplace transform is 1 upon s. Number 2, e raised to at, its Laplace transform is 1 upon s minus a. Number 3, e raised to minus at, its Laplace is 1 upon s plus a. Number 4, cos at, its Laplace transform is s upon s square plus a square. Next is number 5, sine 80. Its Laplace transform is 1 upon, sorry, a upon s square plus a square. Number 6, cos hyperbolic 80. Its Laplace transform is s upon a square minus a square. Next function is number 7, sine hyperbolic 80. Its Laplace transform is a upon a square minus a square. And last is number 8, t raised to n. Its Laplace transform is n factorial upon s raised to n plus 1. So we have to remember these 8 formulas only, along with the definition of Laplace transform, to solve any type of problems which are involved in this topic. So remember this one. Now let us see the problems depending on Laplace transform, how to find Laplace transform. So see the first problem, find Laplace transform of f of t, that is equal to t minus 1 when 1 is less than t is less than 2, and 3 minus t when 2 is less than t is less than 3, and 0 otherwise. So we have to find Laplace transform of this function. This is discontinuous function, discontinuous in two sub intervals, that is 1 to 2 and 2 to 3, and otherwise we get 0. So see here how to find Laplace transform. So by definition of Laplace transform, we have Laplace transform of f of t is equal to integral from 0 to infinity e raised to minus st into f of t dt. So this is the definition. Now here we can write 0 to 1 e raised to minus st, but 0 to 1 there is no function defined in the interval 0 to 1, so we take this 0 into dt, plus next interval 1 to 2. So in the interval 1 to 2 function is defined as t minus 1, so e raised to minus st as it is into t minus 1 dt, plus next interval is 2 to 3. In that interval function is defined as t 3 minus t dt, plus next interval is 3 to infinity, and in that interval function is not defined, so we can add 0 into dt. Okay, so totally we get integral from 0 to infinity. Now this first integral and the last integral get 0 values. Now we have to evaluate only these two integrals. So using by parts rule, because e raised to minus st is first function and t minus 1 is also function of t, so using by parts rule, this can be written as t minus 1 first function as it is, integral of e raised to minus st, that is e raised to minus st divided by minus s, minus derivative of t minus 1 is 1, and integral of e raised to minus st divided by minus s is e raised to minus st divided by s square, limits from 1 to 2. Okay, plus now we are going to evaluate this integral. Again here 3 minus t is the first function, so 3 minus t as it is, integral of e raised to minus st is e raised to minus st divided by minus s, minus lower limit, taking derivative of 3 minus t, that is 1, and integral of this function e raised to minus st divided by minus s is e raised to minus st divided by s square, limits from 2 to 3. Okay, so this is the integral. Now we have to put upper limit as well as lower limit. So if we put upper limit and lower limit, we can write, so here if we put upper limit 2 minus 1, that is 1 into e raised to minus 2s divided by minus s. Here minus as it is e raised to minus 2s divided by s square. Now if we put lower limit here, so 1 minus 1, that is 0, so this term gives 0 value. This minus and lower limit minus, we get plus e raised to minus s divided by s square. Okay, now this completes your first term. Now concentrate on second term. So if we put upper limit here, we get 3 minus 3, that is 0, so first term gives 0. Now this is minus. If we put upper limit, we get e raised to minus 3s divided by s square. Now if we put lower limit here, 3 minus 2, that is 1, and lower limit minus, we get minus e raised to minus 2s divided by minus s. And if we put lower limit here, this minus and lower limit minus, we get plus e raised to minus 2s divided by s square. Okay. Now see here which term you first cancel. So this term with this term with this will get cancelled. So what remains? E raised to minus s minus e raised to minus 3s divided by s square. So this is your required Laplace transform of given function. So this is the procedure how to find Laplace transform of any type of function. Now see one more problem. How to find Laplace transform. See, next problem. Find Laplace transform of f of t is equal to t minus 1 and 7 when 2 is less than t is less than 3 and when t is greater than 3. So again this is discontinuous function. Function is defined in two intervals, 2 to 3 the first and greater than 3 is the second interval. Okay, so see how to find Laplace. So again by definition of Laplace transform of f of t is equal to integral from 0 to infinity e raised to minus st f of t dt. So this can be written as integral from 0 to 2. In that interval function is not defined, so we get e raised to minus st into 0 into dt plus second is 2 to 3. In that interval function is defined as t minus 1 into dt plus next is 3 to infinity. In that interval function is defined as 7 e raised to minus st as it is into 7 dt. Okay. Now this integral gives 0 value. We have to evaluate only these two integrals. So evaluating this, we can write using by parts rule. First function t minus 1 as it is. Integral of e raised to minus st is e raised to minus st divided by minus s minus derivative of t minus 1 is 1 and integral of e raised to minus st divided by minus s is e raised to minus st divided by s square. Limits from 2 to 3 plus here 7 is constant and integral of e raised to minus st is e raised to minus st divided by minus s. Limits from 3 to infinity. Okay. Now substitute upper limit as well as lower limit. So if we put upper limit, we get 3 minus 1, that is 2. So 2 into e raised to minus 3s divided by minus s minus. If we put upper limit here, we get e raised to minus 3s divided by s square minus. Now if we put lower limit, so 2 minus 1 is 1 into e raised to minus 2s divided by minus s. This minus and lower limit minus with plus e raised to minus 2s divided by s square. Okay. Now this completes your first term. Now here plus 7 into e raised to upper limit, that is to minus infinity, that is 0. And if we put lower limit, we get 7 into lower limit is 3. So we get e raised to minus 3s divided by this minus and lower limit minus, we get plus s. Now try to simplify. If simplification is possible, then see here. This is e raised to minus 3s 7 times and this is 2 times with negative sign. So totally we get 5 times. So equal to 5 times e raised to minus 3s divided by s. Again this e raised to minus 3s upon s square as it is minus e raised to minus 3s upon s square as it is minus plus e raised to minus 2s upon s as it is plus e minus 2s upon s square. So this is your required Laplace transform of given function. Okay. Now see, this is a complete procedure to find Laplace transform. Now these are the two problems in which we have to use definition of Laplace transform to find Laplace transform of given function. Now see example of those types in which to find Laplace transform we use directly the Laplace transform of elementary functions. Okay. Now see the next problem. Find Laplace transform of cos square t. Find Laplace transform of cos square t. So see how to find Laplace transform of cos square t. So Laplace transform of cos square t, that is nothing but Laplace transform. We have to use formula for cos square t. What is formula for cos square t? That is 1 upon 2 into bracket cos 2t plus 1 bracket close. We know the formula. Okay. Now 1 by 2 is constant. Taking outside, Laplace transform of cos 2t plus 1. It is 1 by 2 as it is into bracket. What is Laplace of cos 2t? Laplace of cos 2t, a is equal to 2 here. So we have s upon s square plus a square. A is 2, so here we get 4 plus. What is Laplace of 1? That is 1 upon s. Complete. So this is your required Laplace transform of cos square t. So this is the simple method or very short method to find Laplace transform of any type of function by using directly the Laplace transform of elementary functions. Now see one more problem. Find Laplace transform of t plus t square plus t cube. So this solution is Laplace transform of t plus t square plus t cube is equal to Laplace transform of t plus Laplace transform of t square plus Laplace transform of t cube. Now using formula for Laplace of t raised to n. So Laplace of t raised to n is equal to 1 here. So we get n factorial, that is 1 factorial divided by s raised to n plus 1, that is 1 plus 1 plus t square. So n is equal to 2 here. So we get 2 factorial upon s raised to 2 plus 1 plus 3 factorial upon s raised to 3 plus 1. So that is equal to 1 upon s square plus 2 factorial is 2 upon s cube plus 3 factorial is 6 upon s raised to 4. So this is your required Laplace transform. So these are the simple problems by using the Laplace transform of elementary functions. So in this lecture we have to discuss only these parts: how to find Laplace transform by using definition, or how to find Laplace transform by elementary functions and using by Laplace transform of elementary function. So this completes your first lecture. Thank you.